Hello everyone. In this video I'm going over a few examples from a particular textbook in which we're going to be modeling a situation with first order differential equations, and these are specifically about population growth, or you might also see radioactive decay problems, but for the most part my examples have to do with population growth examples. So let's take a look. I didn't write them out this time, I just kind of brought them up on the screen here. So, first example I want to go over. The population of a community is known to increase at a rate proportional to the number of people present at time t. Alright, so let me just start off by making a model for this. Get rid of this site there and describe what's being described there in that first sentence. So let's suppose, just because in a lot of other examples, we consider y as the dependent variable, I'll use y again. Or maybe how about this? No, instead of this, how about p for population? And p depends on time here, right? I did mention a time t. So I'm going to have this function called p of t, which is going to be the population of a community at time t. So, people present in this community at time t. All right. Now in that first sentence, it says the population of a community is known to increase at a rate proportional to the number of people present at time t. So that means that the rate, remember anytime you hear the word rate, it's derivative, right? A rate of change, an instantaneous rate of change. So here we have, like in that first sentence, this is dp dt. This is the rate at which the population changes over time with respect to time. The rate at which population changes with respect to time t. And they are telling us that this is proportional. Right? This rate is, right, equals, and then proportional to the number of people present at time t. So proportional to p of t here, or just I'll call it p. So, well, no, they didn't say, if they don't say directly proportional or inversely proportional or jointly proportional, typically if the word directly is not there, it's just assumed to be directly in most cases. Not always, but. So there's going to be some sort of constant of proportionality times, the amount of people present at time t. All right, so k, right, k is the, constant of proportionality. And, saying that dp dt equals kp, like this, tells me that this rate is proportional to p. Is proportional to the amount of people present at time t, right? So there's our differential equation. And we'll be solving that in a second. Right? We'll see that it is separable. All right, so pulling the problem back up, it says after that sentence, if an initial population p sub 0 has doubled in 5 years, how long will it take to triple, to quadruple? All right, so we're told that the initial population is some number, p sub 0. All right, so let's use that. So we have an initial condition. So that kind of makes this, that it turns this into an initial value problem in a way. So we have an initial value problem, IVP, and the initial condition given to us is that, the population at time 0, right, the initial population, they're calling this p sub 0. All right, so again, some unknown value, but there's your initial population. Now the information given to us, they're saying, if this initial population has doubled in 5 years, how long will it take to triple? All right, so I'm gonna mention that here, the information given. This doubles in 5 years. All right, so let's just assume here that t is in years. And what does this mean? To say that it doubles in 5 years, that means that p of 5 would be just 2 times p sub 0. Right, double p sub 0. Alright, so we have enough information now to be able to solve our differential equation first off. And then we can use an initial condition, and maybe both of these conditions actually, to find the value of k, right, the value of our constant of proportionality. And then once we know this value of k and the solution, our solution to this differential equation, then we can answer any question they want about this population growth. Alright, so that's what I'll start with. We'll solve the equation. So one, I'm solving the differential equation. And dp dt equals, some constant k times p. Alright, and again, you can think of this is separable. You could also, this is a first order linear differential equation. Right, this is a first order and it's linear because the coefficient on the p prime and p itself are dependent on at most t, or just constants really. So you could either separate the variables, or you could put it in the standard form for a linear equation and solve it, using an integrating factor. Do whatever you like. All right. Me personally, though, I'm just going to say, hey, this is easily separable. Right? Put the p's on one side. You got dp over p equals, and then k times dt. Separate, and again, this manipulation. Remember, you can only do this kind of manipulation. Treating these quantities like a fraction. You can only do this with first order differentials. Then I integrate both sides. Indefinite integral, we have the natural log of the absolute value of p over here equals k times t, and then plus some constant, and I'll call this c1, because I'm going to change it in a minute. So c1 is a constant, our constant of integration. And then to solve for the population function p, I just exponentiate both sides, base e, so we have p of t, or just p, will look like the following. E to the kt, right, times e to the c1, but e to the c1 is just another constant, so I'm going to call that capital, another big C here. Right, so again, capital C. This is different than C1. Right, C is constant. Okay, so here's the model we're using. And then to answer any question they have for me, I'm going to want to fill in this model. All right, I want to find the value of this c and the value of this k that correspond to this particular scenario, this particular example. All right, so I'm going to find the values of c and k here, fill in the model. All right, well, the c is simple enough. I can use my initial condition. Remember that p of 0 was this p sub 0 number. Right, p of 0 is this p sub 0 number. So I go to my equation here, replace t with 0. And what would p of 0 be? That would be c times e to the k times 0. And this must be equal to this p sub 0 number. And then we can see from this, we have e to the 0 power is 1. So the c, the value of this constant, must just be p sub 0, the initial population. Right. So now the model looks like this. Right. P of t equals p sub 0 times e to the kt. Right, and now all I need to do is figure out the value of this k, right, this other constant. And that's where the other information comes in. Right. The other information they gave us was that this initial population of p0 doubles in 5 years. So we also know that p of 5 is just 2 times p sub 0. And that gives me another equation to solve, where I can solve for the constant k. So I go through I go through my model here, replace t with 5. Now p of 5 would simply be p sub 0 times e to the 5k. And this should be equal to 2 times p sub 0. Alright. And you can divide both sides by p sub 0. That gives me e to the 5k equals 2. Take the natural logarithm of both sides. That'd be 5 times k equals the natural log of 2. And then finally divide by 5. Right? So k, this constant of proportionality, is the natural log of 2 divided by 5. Or if you'd like, using a property of logarithms, you could say it's the natural log of, and then 2 to the 1/5 power, if you want to do that. Same thing. They're the same thing. Alright, so now I can totally complete the model for this population growth scenario, putting in that value of k. So now the model looks like this. The population at time t equals p sub 0 times e to the kt. Right? So I'll put the natural log of 2 to the 1/5 power times t, and again, you can leave it like this if you wish, or the natural log of 2 divided by 5 and then times t, whatever you want. But I can see a way to simplify this as well. Again, using properties of logarithms, this is p sub 0 times e to the natural log of 2 to the 1/5 t, of 2 to the t over 5 power, putting in the t as in the exponent inside the logarithm. And then e to the natural log of something undo one another. So my final model, again, you can use this model here, but I like this one personally because there's no e's in logarithms. So the population at time t is, the initial population, p sub 0, times 2 to the t over 5 power. And this is the model I will be using to answer any questions they may have. All right, great. So now the question was, it's been a while, let me pull that back up. How long will it take for the population to triple and then to quadruple? So now that I have my model fully completed, answer their questions. I'll say how long to triple the initial population. So we're just basically solving this equation. That's when, for what value of t is the population going to be equal to 3 times the initial population. All right, when is p of t going to be equal to 3 times p sub 0? And how many, t is in years here. Now be careful, t is in years here for this problem, but it might be in days or minutes or months or whatever in other problems. Anyway, so p of t, my model is this. So we're solving this equation, p sub 0 times 2 to the t divided by 5 power equals 3 times p sub 0, and then it's a simple matter of solving an exponential equation. Right? So I divide through by p sub 0. We have 2 raised to the t divided by 5 power equals 3. And if you want, you can do log base 2 or do natural logarithms, because most calculators have a readily available natural logarithm. So I'm going to do this, and then you can pull the t over 5 out using some properties of logarithms. I am not going to go over the properties of logarithms in this video. So we have t over 5 times the natural log of 2 would be equal to the natural log of 3, and then multiply by 5 over the natural log of 2. So t equals 5 times the natural log of 3 divided by the natural log of 2 years. This is how long it would take to triple the population. Now let's approximate this. Let's pull out my calculator here. I don't know how well you can see this, but the natural logarithm button is on the left there. This is a TI-84 plus. And I'll do the natural log of 3 times 5. Sorry if this is tiny. And then divided by the natural log of 2. So approximately 7.9 years. Right, so a little under 8 years to double. And then what if I change this to quadruple? Well, that doesn't change all that much. I mean, the only thing that would change, the 3 becomes a 4, right? So I can tell you right now, the time it would take for the initial population to then quadruple would be 5 times the natural log of 4 divided by the natural log of 2, which really is just 10 years. Because this is 2 squared, you could pull the 2 out front, make it 10 times the natural log of 2. The natural log of 2 would cancel. And just to double check that, 5 times natural log of 4 divided by natural log of 2 is 10. Right? Okay. Wonderful. Alright, so we got our answers there. Alright, so that was number 1. That was my first example. Then the second example. Hopefully this all made sense so far. It's number 2. I'm just going to go down the first 3 here. So suppose it is known that the population of the community in problem 1 is 10,000 after 3 years. Then what was the initial population p sub 0? What will be the population in 10 years? And then finally, how fast is the population growing at t equals 10? Alright, so first things first, let's get that. We have a new condition here. Alright, so I'll put the model up. Right? It said from problem 1. So just going back on my page here. So we still have this same model that has not changed. So it's the model from problem 1. All right. But now we know the following. We know that the population after 3 years, right? So P of 3 is equal to, 10,000. And then they're asking, what is P sub 0? Well, and I'll probably, just round to the round to the nearest person, because this is a population of people in a community. So really I'm just solving this equation, right, for P sub 0, because what is P of 3? Going through my model from problem 1, that'd be P sub 0 times 2 to the 3/5 power, right, replacing t with 3. And this needs to be equal to 10,000. And then we solve for P sub 0 very simply. Dividing, 2 to the 3/5 is a number. Maybe whatever the 5th root of 8 is. And then, just divide by that number. So P sub 0 be 10,000 divided by, whatever 2 to the 3/5 power is. So again, I'll put this in my calculator. So 10,000 divided by, and then 2 to the point, I'll just put 0.6 power for 3/5. It's closer to 6,598. It's 6,597.539, but again, we're talking people here. So I'm just going to round to the nearest person. Right? So it's approximately, if you round to the nearest person, be 6,598 people. Okay. Approximately. Alright, so great. If we had that condition, if there were 10,000 people after 3 years in this community, the initial, and it grew at the same rate and everything as in problem 1, then the town would have started with this many people, about, right, 6,597, 6,598. All right, so that was one question. Now, what I'm going to do is, just so that my other answers are more accurate, I'm going to use this here, the 10,000 divided by 2 to the 3/5. I'm going to use that as P sub 0 to fill in, put it into the model. So now the model looks like this. P of t equals P sub 0, which is now this 10,000 divided by 2 to the 3/5 times 2 to the t/5. And doing some simplification here, this would be 10,000 times, and then 2 raised to the t/5 minus 3/5, right? You divide two things with the same base, you subtract their exponents. So that'd be t minus 3 over 5, right? T/5 minus 3/5. Okay, so now I'm going to use this model to answer the following questions. Alright, so the question now is, based on this information, what is the population in 10 years, right? When t equals 10. So what's P of 10? Is simple enough, right? Just replace t with 10 here. So this would be 10,000 times 2 to the 10 minus 3 over 5, so 7/5. Right? So 10,000 times 2 to the 7/5. And again, I'm since this is people, can't have like a fraction of a person living. I'm going to round this to the nearest person. Alright, so just punching this in my calculator, 10,000, I'm doing it off to the side away from the paper, times 2 raised to the 7/5 power. This is approximately, to the nearest person, approximately 26,390 people live in the town after 10 years. If the initial population was this, and it grew according to the model from the first problem. All right. Then the final question, how fast is the population growing at t equals 10? So the final question is, how fast? Now remember, speed is kind of like a rate. It's a rate of change. So how fast is population growing at t equals 10 at this 10-year mark? Well, recall from the very beginning that the rate at which the population is changing, right, dp dt, is k times p of t. Right? It's proportional to the population at that time. So what was our value of k? Well, k was, remember, k was what? The natural log of 2 divided by 5, I believe. Yes, natural log of 2 divided by 5. That was k. And then times, p of the population at time at 10 years is this 10,000 times 2 to the 7/5. Now that's one way I could have done it. Or take our model here and take the derivative. Right? If you take the derivative of this, dp dt, or it's an exponential, so it would be itself. So 10,000 times 2 to the t minus 3 over 5. But then times, the natural log of 2, and then using the chain rule times a fifth, because, the derivative with respect to t, this would be a fifth up here. So times the natural log of 2 divided by 5, and I get the same crap. Right? And then I plug in 10 for t and get the same thing down here. Now the units on this, right, since it's dp dt, would be people per year. So I punch this in. So basically I'm just going to take my previous answer, the 26,000 some people, multiply it by the k, the natural log of 2 over 5. Right. So the population is changing approximately at a rate of 3,658 people per year. Approximately. All right. At the time when t equals 10, right, at the 10-year mark. Because that will change. You see how dp dt is a function of time, so it will change from year to year. But at year 10, the rate at which the population is growing is approximately 3,658 people per year. Okay. All right, so those were problems 1 and 2. Again, hopefully this is making sense. And this is probably all very similar to something you probably saw this in Calc 1 as well. Right? I'm sure exponential growth and decay was discussed in Calculus 1 at some point. And then finally, my last example. Now this is a totally different example, than 1 and 2. So I'm going to start over. So here we have the population of a town grows at a rate proportional to the population present at time t. So that is the same model, right? It's the same differential equation that I had in problem 1. All right, so let me pull that up. So again, I'm just going to have p be the population at time t, and this is saying again that dp dt is k times p. Right, is proportional to the population present at time t. And we saw already, when you solve this equation, P of t is just, some constant times e to the kt power. Right? Okay, so I'm not going to go through solving it again. All right. The initial population of 500. All right, so they're telling us that the initial population is 500. All right, so basically, like in the previous problem, that means that this constant c I have here is going to be 500, right? Just replace t with 0 and you'll see that. All right, so now the model looks like this. P of t equals 500 times e to the kt. Now all that's left to find is this k, and then I can answer really any question they want. And that's where this next part comes up. The initial population of 500 increases by 15% in 10 years. Well, 15% of 500 would be what, 75? Right, because 10% is 50, and then half of that is 25. Add those together, you get 15% is 75. So that part is telling me this condition, that the population in 10 years is 575. That's 15% increase. All right, and then plug in 10 for t. What is p of t here? We'd have, so 500 times e to the 10k would be equal to 575. And solve for k here. We'd have, so e to the 10k equals 575 divided by 500. Okay, well, let's see, that would be 115 divided by 100, so this is 1.15. All right, 575 divided by 500 would be 1.15, and then natural log of both sides. We have 10k equals the natural log of 1.15, and then divide by 10, so k equals the natural log of 1.15 divided by 10, or if you'd like, the natural log of 1.15 to the 1/10th power. Right, same deal. So now my model looks like this. The population at time t is equal to 500 times e to the natural log of 1.15 to the t over 10. Right, I'm just putting the t inside already, and then again the e and the natural log undo one another, and I got 500 times 1.15 to the t divided by 10 power. All right, so I'm going to use this model to answer any other questions they may have. All right. The question is, what will the population be in 30? What will be the population in 30 years? So I'm just replacing t with 30. All right, so p of 30 would be 500 times and then 1.15 to the 3rd power. Right, because if t is 30, this would be 30 divided by 10, which is 3. And it's another thing where it's a population of a town, so again I'm going to round to the nearest whole number, right, the nearest person. So we have 500 times and then 1.15 raised to the 3rd power, about 760 people would be in this town after 30 years. And then the final question, how fast is the population growing at this time? And remember, the rate at which the population is growing, the dp dt, is proportional to the population at the time. It's just k times the population. So at this time, dp dt would be, kp, which is, the k was the natural log of 1.15 divided by 10 times, and then the population at this time was 500 times 1.15 to the third power, and we get approximately the following. Natural log, and that's approximately, rounding to the nearest person, around 11 people per year is the rate at which the population is changing at this moment. So again, very similar to numbers 1 and 2, just, very quickly. Alright, so again, hopefully not too crazy. Very easy separable equation to start with these population growth or radioactive decay or whatever exponential growth and decay problems, all starting with this pretty basic differential equation here, very easily solvable. Okay, so hopefully watching me do these couple examples help you out when you're working on problems similar to these on your own, and thanks for watching.